there's this sort of freckle-like pattern which appears very random. And the reason for that is the theory we use to describe what the CMB should look like has inherent randomness built into it. So the fluctuations in temperatures that we see arise from what are known as quantum field fluctuations. And so we have a model that describes it called the standard model of inflationary cosmology. So Dr. Hogan has a proposal that kind of aims at changing or maybe tackling the quantum mechanics of inflation. You can think of the CMB as sort of a snapshot of some of the information telling you about the quantum mechanics of in the early universe. Now, the name of that hypothesis is the spooky inflation hypothesis, which is appropriate because we actually submitted a paper like on Halloween about this. And so, regarding the quantum field fluctuations I mentioned earlier, in this spooky inflation model, that's still there, it's still the same. But we're adding a new layer of structure on top of that. And we're doing that in the form of quantum entanglement. So instead of the quantum field fluctuations being the only thing that give you this pattern structure, now there's a new correlation between different points on the sky, which is achieved through quantum entanglement, through some model that I'm not going to get into, but if anyone's interested, there's some theory papers that I'm going to reference later on. But the important thing to get out of this is, since we're adding new statistical constraints on top of the randomness in the CMB, that introduces new statistical consequences, which potentially has measurable effects. So to describe what those measurable effects are, I need to talk about the test that I want to use to make that statement. The test that we're going to use is known as the two-point correlation function. So for those of you who aren't familiar with what this is, I'm just going to explain what it is by telling you how you calculate it, because that was the easiest way for me to understand what it was. So you can imagine the CMB as essentially being assigning a temperature to each point on the surface of a sphere. Because essentially what you're doing is you're looking at a distance 13.7 billion light years away and measuring the temperature at each point in every direction. So for now, we're going to consider 2 points that on the surface of that sphere that are separated by an angular separation of theta degrees. And of course, each of those points is going to have an associated temperature. All we're going to do for now is take those two numbers and multiply them together, and I'm going to keep track of that number in the bottom left. So I'm just going to move over a little bit. Now what we're going to go and do is find every other possible pair of points with the exact same angular separation of theta degrees, take those numbers and multiply them, and I'm just going to keep track of all of those numbers. And then once we've gone through and done this for every possible pair of points with that angular separation, we're just going to take the mean of those numbers, and then that gives you one data point in what's known as your two-point correlation function. You can do that for all of the angular separations between 0 and 180 degrees, and eventually you can get some sort of plot, and this is just some artistic representation of what you might see. So, in the context of spooky inflation, there's two key predictions that we can argue that we can make. One of them is that for 90-degree separations, the correlation function should have a value of exactly 0, with no cosmic variance, which is a very strict statement. So it's actually very easy to falsify because of the nature of it saying that the value is 0 or the theory is wrong. The other thing is that there's expected to be significant negative correlation at 180 degrees, but we focused mainly on the 90-degree one because it's the cleanest statement. And if you want to see more about that, you can check out these two papers on the archive. But I think that's all I'm going to say about it for now. So, how does this shape up to the standard model that I mentioned earlier, which is very well established and like very okay. So it's standard model is good. I'm not saying anything bad about it. Since there's randomness in what you can see in the CMB, you can calculate the correlation function for each of a bunch of simulations of it. And if you do that for lots of simulations, you can plot a graph that looks like this, where the black line in the middle is the average of all of those functions, and then the shaded areas are the 1 and 2 sigma deviations from the mean. So you can see clearly that the standard model predicts that at 90 degrees, the expectation value is going to be less than 0. And at 180 degrees, we're actually expecting positive correlation. So this plot's actually taken from a paper that was written 10 years ago by the WMAP team. And this is the only time that the WMAP team, I think, published a plot for the two-point correlation function. And this thick black line represents the experimental data. And you may notice that it looks suspiciously clean that around 90 degrees, it looks very close to zero. And at 180 degrees, which is a little bit more statistically significant, is that it's pretty much almost like on the edge of the 2 sigma deviation from the mean. So it's that is already pretty surprising. Now, WMAP wasn't the only team to measure the CMB. So it would be inappropriate for us to ignore one of the other giants, which was the Planck collaboration. So the next thing we did after this was look at what Planck published. And then we got a little bit confused. So it's well known that WMAP and Planck agree with each other very well. But when we looked at Planck's published plots closely, we noticed that at 90 degrees, while WMAP looks very close to zero, now Planck is extremely clearly above zero. And we're very interested in what the value is at at 90 degrees. So we wanted to know what the true value was and dig into this a little bit deeper to understand what was going on. You'll also notice that in Planck's published results, they show that at 180 degrees, there's significantly less negative correlation. So those are 2 surprising features.
Sure, just this black line is the data, and
the
band is a lambda CDM prediction?
Yeah, these are all lambda CDM simulations. The thick black line here is experimental data.
So there are error bars, I guess, then on the data.
Yeah, but they didn't publish those. I mean, because so in this standard, from the viewpoint of the standard model, all this stuff is incredibly uninteresting. There's no reason why you should see anything in the correlation function other than it should be very high at 0 degrees because a point is correlated with itself.
Yeah, I was curious about whether
right.
the 2 consistent there.
Something else I want to point out is you'll notice that there's multiple colors on this plot. Basically, Planck has 4 public released data sets where they did 4 different foreground subtraction methods, and that's why there's actually 4 plots from experimental data published here, but I'll get into that later. So,
can I ask a question? So you said initially that, so if you take the Fourier transform of this correlation function, that's the power spectrum, but you said the power spectrum is the same.
Yeah, the power spectrum for like in the view of the spooky inflation isn't changed by adding the new correlations.
But the power spectrum and the correlation function are linked together.
I mean,
in this sense.
I mean, they are. I mean, they're linked together, but it's more like you can get to the power spectrum from the CLs, but you can't go from the power spectrum to a unique correlation function.
That's true.
So I mean, that's basically it's just further statistical constraints.
You're right.
So okay. From this point on, the first thing we wanted to do was see if we could reproduce what WMAP and Planck got because they released their data publicly. So I just went to their websites and downloaded it, ran my own algorithm, and that's what I'm showing on the right. So again, we ran our own simulations. We got a similar spread for the realizations of the CMB. The orange line is one of Planck's pipelines. It's the first one alphabetically. That's why it's the one that I chose to do first. And then the blue line is WMAP. Now you'll notice maybe that now it looks like there's pretty good agreement between Planck and WMAP. And in fact, at 90 degrees, it's suspiciously close to zero. And then things start to deviate around 180 degrees, and that hasn't been explored very much. But overall, very, very good agreement, it seems. But moreover, it seems to be agreeing with what WMAP published in their original publication. So this was a little bit confusing, but also, okay, cool, they seem to agree with each other. But we need to understand why this is happening, because it is a slightly different result. It turns out that the difference came into play with masking. So you can imagine that if you're measuring something that's really, really far away from us, you're going to have contamination in the foreground. Now, of course, both WMAP and Planck spent a lot of effort developing pipelines that could be used to eliminate as much foreground contamination as possible, but no matter what you do, there's always going to be some mistakes or some errors. Now, if you're very confident that some of the points in your CMB have contamination, you can just ignore them, and you can accomplish that by masking it. So in this figure, this is a sample mask where you're removing about 30% of the data points. Now, yes, that's quite extreme. And you can imagine that when you're doing a statistical measurement that averages over lots of points, getting rid of information like this is going to shift your correlation function. So basically, at this point, we didn't know what this was going to happen if we masked it, but I kind of just got lucky. I downloaded this mask from Planck's website, and then I applied it to all of the maps, and then I was able to reproduce what Planck got. Basically, at 90 degrees, if you mask everything like this, the correlation jumps up, and then there's less negative correlation at the end. So one of the cool things about this is, I mean, I'm doing this for WMAP and Planck data, and they're all sort of just lying on top of each other. Now, I want to take a moment to appreciate the fact that WMAP and Planck are completely independent satellites. They measured the same thing, but they did it with different methods completely. They used different foreground contamination subtraction techniques, and there's a stunning agreement between them, at least in the regions in yellow. So that's really impressive. But what we were interested in is what the value is at 90 degrees. And we believed that removing this much information would skew the results in a way that we wouldn't know how to, we wouldn't be able to understand without doing further stuff, which I actually have at the end, but I'm not going to put in the main part of the talk. So the thing is, we decided to just choose a slightly smaller mask and see what that did, because most of the contamination should be in the middle, where the galaxy is. And doing that already got us a lot closer to what WMAP produced in the first place. But we went all the way, removed the mask entirely, just to see what that would do. And now we were greeted with still good agreement, at least for some of the pipelines, but there's this red line which is really jagged and it looks quite anomalous, especially at 90 degrees. I've got to zoom in a minute, but I can explain why that looks anomalous. For now, I want to zoom in at 90 degrees and see what's going on. So here what we're doing is taking a look at a small band around 90 degrees, and these measurements, I mean these numbers for the correlation function are from -10 to +10 microkelvin squared. So these are really, really tiny numbers. Now, I want us to focus on these three lines. The blue one is WMAP, the orange one is the Commander pipeline from Planck, and the purple one is the SMICA pipeline. So these three agree within 0.8 microkelvin squared of each other, and they're completely, and so it's a really, really, really stunning agreement between two different experimental measurements. So the next thing that I need to mention is we looked at Planck's, one of Planck's papers where they discussed some of this stuff. And we can quote from that paper that for large and intermediate angular scales, Commander, aka the orange line, is the preferred solution. And that for observations in temperature, the purple line is also recommended to be used. So taking their recommendations and just focusing on these lines in the middle, we find that there's this really, really, really good agreement. And even if you include the green line, I think the band is only about, this goes up to about 2 microkelvin squared, so it goes from -0.22 with 0.21 all the way up to 2. So it's still really tiny. But the ones that we were told to trust give us like astounding agreement. And also, I should mention, it creates a band around 0. And how around 0 is it? Well, if you take the mean value, it's 0.19 microkelvin squared. So it's super close to 0. And the band is only 0.8 microkelvin squared in width. So it's just very consistent with 0 is the bottom line. Now, I mentioned that there was that red line which was anomalous. And the easiest way to show you why it's so different is to show you what the actual CMVs look like. So this is one of Planck's pipelines. This is Commander. This is another one, the NILC. You'll notice between them, the only thing that really changes is the galaxy area, and that's just because of the different foreground subtraction techniques. This is a third pipeline, and then this is the red one, the anomalous data point. There's very clear contamination in the middle. Basically, if you don't mask this one, don't trust it. So that's why we completely ignored it for the previous slide. And this one, just for fun, is WMAP. If you want, it's a bit more blurred, but that's because Planck was able to get more fine structure in their measurements. So, to basically summarize everything, spooky inflation, pretty cool. I would really like people to argue with Dr. Hogan about it, because it is related to the holographic principle. So it's kind of exciting in the sense that maybe if there's any sort of weight to this, it could be some way of testing quantum gravity experimentally, which would be the coolest thing ever. But I think, yeah, if people challenge the theory, that's good, because then we can get development on it. Experimentally, we were able to show that at 90 degrees, the correlation function is consistent with 0. Whatever the reason for that is, I think that's pretty strange, even if it's not because of spooky inflation, because that's a very clean angle to have a 0. Okay, but yeah, that's basically the whole thing. I have more slides, but I wanted to end here.